This small section, usually I try to include in the first exam, but this semester I couldn't do this. So this wasn't on the first midterm exam, so now we're going to discuss it also. So bridges between the electric field and the electric potential. So if you want to move from the electric field to the electric potential, you remember we derived this formula, right? So you need to, integrate Ex dx from some initial to the final point, and don't forget about the minus. But we didn't integrate this. If you plot integrand versus the variable of integration, then calculate the area. Don't forget to add minus, and that's the potential difference between the final and the initial point. We've done it. It's not complicated, but it's been like more than a month ago, so of course you started forgetting about that. Then if you want to move from the electric potential to the electric field, it's even easier. You just need to take a derivative of the electric potential with respect to the variable, in this case x. And again, don't forget about the minus, because like 15–20% of students forget about that minus every semester. Right. Oh, and if you have a plot electric potential versus x, so it's just a slope, and don't forget to add minus. That's it. Okay, and after that, it's a simple electronics. Okay, simple circuits. So we introduced the idea of the batteries, nothing to discuss. And then we introduce capacitance. So we introduce capacitance in this way. If you have two electrodes, every time they charged with the same amount of charge, but opposite in sign, plus Q minus Q, potential difference delta V. So we introduce capacitance as a charge divided by the potential difference charge of the positive electrode. Don't add them, don't use negative charge, just charge of a positive electrode. So now, whenever you want to analyze a capacitor, you need to think about these three quantities, three parameters, C, Q, delta V, every time. That circuit trinity, I usually call them, right? Just for fun. Okay, then if you apply this definition for a parallel plate capacitor, right? So again, we derived it. We ended up with epsilon naught, universal constant, basically describes electrical properties of vacuum, and times area of the plates divided by the distance between the plates of a parallel plate capacitor. The major feature of this formula, it depends only on the geometry and the material between the plates. That's the major feature. Then, so now we know how to analyze single capacitor. Now what about bunch of capacitors? And we first restricted ourselves to the cases when they're connected in series or in parallel. And in the case when they're connected in series, we derived the formula which can be used to find the equivalent capacitance, just using those reciprocals, right? And again, keep reminding you, don't forget when you calculated this 1/c, don't forget then flip this 1/c equivalent, because again, 5% of students usually forget that. And then, so what's the basically major feature of capacitors connected in series? Basically, it's the test that you need to run in your head in order to convince yourself that they are connected actually in series. Charges in capacitor 1 and capacitor 2 must be the same if they're connected in series. And in the case of the equivalent capacitance, charge in the equivalent capacitor equals to the charges in capacitors connected in series. Okay, and you use this in your quiz, whatever. We already have 7 quizzes. I think it was quiz 6 or 5. Okay, then in case of a parallel capacitors connected in parallel, formula is very simple. And then potential difference across an equivalent capacitor equals to the potential difference across capacitors connected in parallel. So enough of capacitors. Pretty much after that, we started introducing the idea of the electric current and related quantities. So if you have piece of wire, whatever piece of wire, and if you take any cross section, right, and if you sit there and count the amount of charge crossing that cross section per unit time, that's what the current is. So if you measure amount of charge dq over infinitesimally short period of time, dq divided by dt, this is the definition of instantaneous current. Right, then we introduce resistance, basically Ohm's law. If you play with the potential difference and current, their ratio will be all the time the same, right? So that's how we define the resistance of a resistor or conductor, right? Then we also introduce current density. If you take current and divide by the cross-sectional area, perpendicular cross-sectional area. That's what by definition current density is. So then after that, we decided what is sort of anatomy of this resistance. So let's look inside on which parameters that R can depend on. And we found that it depends on the resistivity. Open the book, right? And if some resistivity is needed in the problem, of course, I will provide it, unless the question is about finding resistivity. Then, proportional to the length of the conductor or resistor, usually we assume it has a cylindrical shape. And divided by the cross-sectional area of the resistor conductor. Okay, that's enough. And after that, we discussed electric power. Since we don't use electric form of energy in our life every time we transform, of course, it's logical to ask the question, how fast do we transform this electric form of energy into something else, right? So, and we derived that power equals the product of the potential difference and the current through the device, or I squared R, or delta V squared over R. We just discussed it like a couple of classes ago. Then, after that, equivalent resistance, very similar to the method of an equivalent capacitance. Very similar, just formulas are flipped. If resistors connected in series, then this is the formula which we need to use to find equivalent resistance. Usually students have no troubles doing that, but troubles over here. So current in the equivalent resistor equals to the currents in the resistors connected in series. Again, these formulas will be in the formula sheet attached to the exam paper, so you will be able to find it right. In a parallel case, this is the formula, reciprocals, and now potential difference across an equivalent resistor equals to the potential difference across resistors connected in parallel. So after that, since method of an equivalent resistance is significantly limited only to these cases, parallel and series. It's series limitations. So then we introduce Kirchhoff rules, which are universal. It doesn't matter which circuit you have, doesn't matter how complicated or easy it is, you can apply them because there are two fundamental laws lying behind them, conservation of charge and conservation of energy. So if you have any junction point, the total amount of current entering junction point must be equal to the total amount of current leaving. And then loop rule, if you take any loop in the circuit, walking around in the same direction, counting all the potential differences, when you get to the starting point, you must end up with 0. Great, and after that, RC circuits, just recent stuff. Let's just quickly review, and then we will start solving problems. So RC circuits where you have a resistor and a capacitor, and there are two situations. You charge that capacitor, or you can discharge that capacitor, so if it is already full. In the charging case, I, it's a current in the circuit, Q, it's a charge inside of the capacitor. So we derived all these functions. Capacitance, charge inside of the capacitor increases sort of like this, almost like a log function, but it's not a log. So it's a Q naught 1 minus E to the power of minus T over tau. Tau appears naturally during the derivation. It's a RC time constant, very important parameter, which tells us how fast this or that RC circuit charges or discharges. If tau is small, it means it charges or discharges faster. If it's longer, then it charges and discharges slower. Then current can be found from the charge by differentiating. And if you do it, you will end up with this formula. Current decays exponentially. And if you don't remember how it behaves, remember we watched the movie that Far and Away, that episode, Land Run. So it can help to restore the sort of structure of the function. And then potential difference across the resistor, just Ohm's law, because now you know the current, resistance usually given, so you can find it. Potential difference across the capacitor, you can using a definition of capacitance. Very, very straightforward, reasonably. Right, in the discharging case, capacitor is full, and then it gets discharged through the resistor. Charge decays exponentially, almost like here, right? Current decays also exponentially. When you close the switch at the initial moment of time, current is the maximum possible, right? And again, the same time constant. So pretty much this is the scope of the exam, right? And now let's solve a few problems. Okay, so the migration. So the first problem. I will start from this corner, and I will keep moving, almost discussing almost everything. And I'm afraid of tripping over here. If I kill myself, call my friends, right? Over here. All right, so the problem number 1. So let's move back and forth between these two quantities, electric field and the electric potential. So this situation is given. So let's say we have the electric field, E sub x. Units, it's either newtons per coulombs, like what we had at the very beginning, or now volts per meter. Yeah, it is in focus. Good. Right, and let's say this is our x-axis, right? X in meters. And the plot. Okay, you know what? No, first I will plot it and then I will put points. I think it will be easier. Right. So straight line. And so this is 0, then 1, 2, and 3. Right. 3 points. And value of electric field minus 100, and then over here at 3 points, I mean at the point 3, we have 200 volts per meter. Right. Yeah, that's it. So this is information about the electric field, and additional piece of information is given. So electric potential at x equals to 0 equals to, I don't remember what, minus 50. Minus 50 volts. So essentially over there, V equals to, minus 50 volts. So plenty of information about the electric field. We need to get information about the electric, we need to find electric potential at point 3. Find a V when x equals to 3 meters. Okay, we solved similar problems, but again, it was like over a month ago, so we need to refresh that. So this is the bridge from E to V, so we need to take care of that integral. So it's a, let me first rewrite it, so it's a delta V equals to V final minus V initial equals to minus integral from x initial to x final E x dx. So general formula, right, which can be applied for any situation, in this case, one-dimensional situation. And as the first step, of course, we need to make a decision which point is initial and which point is final, right? Initial and the final point. And in this case, choice is kind of obvious. Since some information is given about the electric potential at x equals 0, so it makes sense to take that point as our initial point. So let x equals 0 be our initial point. And then since we want to find the electric field at electric potential at point 3, so we will take that as final point. Be our final point. Right. Okay, so now after that, we can say we adjusted this formula for our case, and we can write down delta V. So delta V equals to V final, it's a V, I will use subscript 3, just to write slightly less. V sub 3 minus V sub 0, right, and equals to minus integral from 0 to 3 Ex dx. I just rewrote it, adjusting for our situation, nothing fancy. And of course, now we can use that trick which we discussed in the lecture. So the value of this integral is just the area under the curve. Right. So I can write it is equal to minus and area. Which area? You know what? I'm going to split. First, I will show. Of course, it's this area. Right. So let me maybe label points. Okay, this is O. This is which way? Okay, A, B. This will be point B. This point C. This point D. And the last one, what? I skipped A. How come? No, it's so bad. No, I cannot stand this, right? Let me change that. A, B, C, D. Okay, so now we can write this area. So of course we're going to split into two: area of this triangle and area of that triangle. And area of that triangle, will it be positive or negative? Of course negative, right? Because the height is negative. So don't forget about that. So it will be area of OAB and plus area of BCD, right? Okay, and let me close the bracket. Okay, so our unknown is over here. So V0, I will move to that side. Right? So it will be V sub 3 equals to V0 goes to with plus to that side, minus stays, and now area. Area of a triangle, 1/2 times height times base, right? So it will be 1/2. Height is minus 100 volts per meter. Base 1 minus 0, so 1 meter, right? Base of this triangle. So it's a 1 meter. And then plus area of the triangle BCD. Right. Again, it will be 1/2. Height now 200, right? 200 volts per meter. And base 3 minus 1. 3 minus 1. And even if sometimes this triangle can be, part of this curve can be on the negative x-axis, okay, on this side, still the same every time. Final point minus initial point, so pretty much idea is still the same, right? Just numbers are negative. Okay, so now I need to close this bracket, and let's calculate it finally. Again, guys, at any moment, if something not clear in terms of what I wrote or what I said, say something. All right, so this is minus 50. It was given from the very beginning. Minus 50 volts. And then minus minus 50. It's a contribution from this triangle, right? And that triangle, that two goes, and we will have a plus 200. All right. Okay, so what are we getting? Negative 150 minus 50, it's minus 200, right? 200 volts. Minus 200 volts. So it came back, right? We've solved problems like this, very similar. And again, it was a long time ago. Okay, not long enough. Okay, if you don't have questions, then I will move to the second problem. And let me separate it like this. Still have this part of the whiteboard. And the next problem is even easier. Essentially, it's about this bridge. Let's just quickly again refresh it. So this will be problem number 2. Good? Okay, good. So problem number 2. Now let's assume that the plot electric potential versus X is given. Okay, slightly tilted, but still not bad. So electric potential, units of volts, yeah, and then let's say this is our X in meters. Okay, not X, R, but again, so X, R, what's the, as long as it is a one-dimensional situation. It can be Y, Z, whatever. But in this case, it's R. And so, you know what, probably I will start with these points on the X-axis, or R-axis. 1, 2, I need to get 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And the plot. So first it goes straight up from 0 to 0.3. Yeah, over here I also need to, yeah, first I will plot and then I will put those points. Right, over here. Right. Then it goes to -4. So let's say it will be 4, 3, 2, 1, 1, 2, 3, 4, and then 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4. So then it decays to, okay, not decays, just goes down to this point. Along this straight line. So this is, and this is dash line. So within 1 meter, it drops from 4 volts to -4 volts. Sudden drop, and then it stays constant. So that's the plot. Yeah. All right, so we need to find the electric field. E. Of course, it's a one-dimensional case, so we will have to find I sub x. E sub x, not I sub x, E sub x. Right. So since the bridge is this, it's just a negative slope. So let me write that down over here. So E sub x equals to minus dv over dx. Wait, dr. Okay, I decided to introduce a different variable, not x, and keep jumping to the same x. Right, so that's the general formula. And now, so since it's negative slope, and since we have 3 different slopes, of course, it makes sense to divide this curve into 3 regions, right, where slopes are constant. So region number 1, then region number 2, and this will be our region number 3. Right. We've done very similar, but again, long time ago. So the first region, okay, I will write underneath. So E sub 1 equals to minus dv over dx. You know what? And again dx. dr. Okay. At this point, every time, I usually tell this, guys, since we have straight lines, right, and we want to find the slope, so it doesn't matter if you use infinitesimally small increment in the variable or finite increment, in this case in r, it doesn't matter. Slope is constant, exactly the same. So let me rewrite this. First, let me write since since we have straight lines, so I can rewrite it as minus delta v over delta r. Delta v over delta r. So instead of using infinitesimally small, I can use finite change in r. Right? And in the first region, so it means that minus v at 0.3 minus v at 0.0 and divided by 3 over 0. Of course, in meters. And minus in front. So v at 0.3, it's 4 volts. Okay, that's some ugly bracket. 4 volts minus 0 volts divided by 3 meters. So we'll get 4/3 over volts per meter minus 4 over 3 volts per meters. Quick question. What does it mean minus in front of this number? Is it true some kind of negative magnitude of the electric field? Because kind of negative magnitude of the electric field sounds so strange. I cannot imagine that. Right. So what does that minus mean? Yeah, it's a direction. Since it's essentially one-dimensional vector, negative one-dimensional vector just tells us that that vector points in the negative x direction. That's it, right? So it means that over here, I can draw, okay, I will use probably green. So this will be electric field E sub 1, direction of the electric field, right? And so now region number 2. Oh, the slope is large, so of course that is going to be stronger. Right. Electric field going to be positive or negative? For the region number 2. Will be positive because the slope is negative and minus in front, so minus from there, minus from there. Of course, two minuses are going to give us plus, so the electric field over here is going to be positive, right? Pointing in the positive x direction, r direction. Right. E in the second region equals to, now again, minus delta V over delta R. And in our case, it's what? Final point, again, keep track of the final and initial point. Final point minus 4, initial point 4. So it will be minus 4 volts, minus 4 volts. Again, this minus because we're subtracting the final value. And divided by the 4 minus 3 meters, increment in R, 4 minus 3 meters. So what are we getting? 4 volts per meters. Oh, I mean 8 volts per meters. Yeah. 8 volts per meters, right? And so region number 3, what's the value of the electric field? 0, of course, because the slope is 0. Right? Obviously here electric field is going to be 0. So this electric field in the positive direction, so it's a E sub 2. Right, and E sub 3 is 0. Right. Yeah. Why is this negative? This? Okay. yeah, I expected this. Okay, I can rewrite it like this. Okay, I cannot rewrite like this. I'm going to do this. So, delta V. So, this delta V, it's, look. Okay, let me write underneath. So, it will be minus V final minus V initial divided by delta R. Final point, negative 4. And then minus between them because it's delta. We're subtracting the initial value. So minus, so this minus comes from delta, from the definition of delta. And initial point, yeah, plus 4. So it's a minus 4. Okay, minus 4, minus 4. Yeah. Okay, enough of this. Again, these problems are straightforward, not much of a problems usually. Again, among students, but since it was discussed long ago, I felt like we should discuss it. Now, next sort of conceptual question. And I feel like yeah, it will go probably under the same roof of problem number 2. Okay, conceptual question. I'm not going to label it. So let me separate it like this. And conceptual question without number. So now, what if we have, for example, equipotential lines are given? So which way I drew? Let's say this way. So let's say these are our equipotential lines. So equipotential lines. You remember what is so special about equipotential lines? It's a line where the electric points are at exactly the same electric potential. So let's say these points are at minus 10 volts, right? So number. These are at minus, you know what, I don't like that. Let me use different color because it's almost blending like a extension of the line. So let me write it like this. So it will be V1 equals to minus 10 volts to avoid confusions. Then this V2 is minus 15 volts. And with 3, let's say minus 20. And so let's assume that we have 2 points, this and that point. How did I label them? A and B. And by looking at this, I want to extract as much information as possible about the electric field. Essentially, we want to get from information about the electric potential, we want to get information about the electric field. Essentially, it's still this a bridge, right? But now it's a graphical way of getting some information. And we discussed it at the very end before we started moving to simple circuits. So you remember there are 3 pieces of information. And you actually used it in your lab number 2. So first, what's the angle between the electric field and the equipotential lines? They are all the time perpendicular to each other. So let me write that down. Electric field, so first piece of information, E, which way I wrote it, E is perpendicular to equipotential lines. Lines. Right. So it means that the electric field is going to be something like this. Right. Then direction, second piece of information. All right, electric field points in the direction where the electric potential is going down. So pretty much it points downhill. So in this case, electric potential here minus 10, minus 15, minus 20. So downhill it's this way, downhill, right? So let me write that down. So electric field points downhill. Right. Okay, so now I know that electric field is going to point that way. Second piece of information. How can we get information about the electric field strength? It is in the density of lines. Larger density of equipotential lines. Now, density of equipotential lines connected to the electric field strength. Okay, so let me write the last piece. So, number 3. So, electric field, which we wrote, magnitude, is proportional to density of equipotential lines. Okay, so now these are 3 pieces of information. We discussed it in the lecture. Now, after this, I can draw electric field vectors. So perpendicular here, density of lines is larger, so of course electric field is going to be stronger. So vector longer. Here, vector is going to be smaller. So this will be, let's say, E at point A, and this is 90 degrees. Over here, it will be smaller. E at point B. Again, this is 90 degrees. Downhill. Again, we discussed this and we practiced, but again, it was long ago. Bless you. All right, so another conceptual question, but I'm running out of space, so I feel like I need to start erasing something. All right, okay, I will erase this part. So far, so good? Yeah, it's nothing complicated. We just need to refresh it. And we had it in the past. So quite often I give questions like this on the exam. Again, it's a conceptual question, CQ. All right, so what if we have this rectangle? No, square, not rectangle, square. Okay, I do my best in terms of drawing So it's a square. And so let's assume that we have 2-point charges. One is here. Okay, let me draw it here. So let's say minus q, and over here there will be plus q. Yeah. And so we want to get information about the electric field and the electric potential at the center, at this point, right? We again discussed that in our lectures among, okay, yeah, in one of the clicker questions. So electric potential of a point charge. Okay, it's from the exam one. Electric potential of a point charge, it's a K Q over R, right? You remember that? So as a result, what will be the net electric potential at this point, at the center of the square? You're not for my recitation classes, that's why you panic, right? And Nikolai would respond. All right, okay, so we just need to write contribution from this charge to the net electric potential at this point, and from that charge, superposition, principle of superposition. So let me write V at center. It will be equal to V from positive, let me write it V plus, and plus V minus. Principle of superposition for a scalar function, all right? So, and of course, we can write, we can apply that twice. So it's a K, then plus Q over, what's the R? Let's call it this length L. From that corner to the center. And of course, this distance also exactly the same because it's a square. And we're talking about the point at the center of the square. So Q divided by L. And then contribution from this negative charge, it will be plus K. But now charge is negative and the distance exactly the same. What will be the answer? Come on. Two exactly the same terms. Zero. Zero, of course. Come on, two exactly the same terms, right? So you just need to add plus 5 minus 5, right? Of course, you need to see that simplicity, right? Of course, when you see it, you go, damn it, it's so simple, trivial, right? No, it's a normal part of, okay, no. Yeah, part of education, right? Right, okay, everyone sees that. Of course, it's simple. Then we can also add maybe, what about the net electric field? Again, you need to apply principle of superposition, but the thing is electric field is a vector quantity. You have to be careful and need to add 2 vectors. Here it's a scalar quantity. Principle of superposition is essentially banal, very simple. Now let's find electric field at the center. All right, so what if electric field at the center, right? Okay, now I'm not going to write anything. I'm going to draw a picture. Okay, vectors. Okay, contribution from the positive charge to the net electric field at the center. Direction. Upwards, it's this way? Okay, this way, right? Because you remember, what are the electric field lines of a positive charge? Okay, let me show it separately over here, because yes, sometimes students make mistakes over here. So if you have positive point charge, electric field lines are like that. So essentially our point, this point, relative to the point charge, this is our point charge, this is the point. So essentially our point is somewhere over here, right? So you see, electric field must point that way. So it's this contribution. So it's a E from the positive charge. Then negative charge, very similar. If you have a negative charge, just recall the electric field lines. They go towards the negative charge. Right. So our point, this is our negative charge, this is point. So essentially, it's our point is over here. So it means that electric field points that way. So on our picture, It's this. And absolute value of these two vectors, exactly the same. Distance the same. Charges are the same in absolute value. Of course, directions are different, but magnitudes are the same. So now, principle of superposition, you just need to add them up. Of course, electric field at the center is going to point to your right and my left. Quite often I give questions like this. I can add number of point charges instead of 2, 3, or 4. Right. But again, idea is very similar. Enough of this section about the electric field and the electric potential. Make sense? So let me start. Let me erase and move to the capacitor. So that was 1, 2 conceptual questions I didn't count. So this will be number 3. So problem somewhat similar to what we had in our recitation class, but I changed a few parameters. Okay, so there is a parallel plate capacitor. 2 parts. In part A, some information is given, so we need to find the amount of charge inside of the capacitor. In the second part, we're going to reduce the distance between the plates, and again, we need to find the amount of charge. We solved a very similar problem in the class, but there we increase the amount, we increase the distance, now we reduce the distance. Okay, so now it's a capacitor. Problem about a capacitor. All right, and I will probably draw a picture first, and then I will write what is given. So it's a part A. So this is the first plate. This is the second plate. Of course, it's not in scale because it's hardly a parallel plate capacitor. And it is connected to a battery. Right. So EMF, okay, delta V, not EMF. Delta V of the battery is given. Okay, let me write it down. So delta V of a battery, and I don't remember the number, 12 volts. Then area of the plates also given, A, and then distance between the plates will be D1. It's a part 1. I mean, the first part, part A. So I'm going to use subscript 1 to denote quantities from part A. So then what else? Area of the plates I can write above everything. So it's 25 square centimeters. Sooner or later, we will have to convert to meters squared. Let's do it immediately. Because I feel like. So 25 square centimeters, so you need to divide it by 1 centimeter, multiply it by 10 to the power of minus 2 meters, right? And do it twice. So you just need to multiply by 10 to the power of minus 4. So it will be 25 times 10 to the power of minus 4 meters to the power of 2, right? Yeah. Okay, and in part A, you know what, let me write part A over here. So part A, and distance D1 is 2 millimeters. Okay. So we need to find charge. charge in the capacitor in this part A. So nothing fancy. Since we have a capacitor, we need to think about these three quantities, C, Q, delta V, one by one. We need to find information about the charge. So charge we will be analyzed at the very end. Then, so we need to analyze C and delta V. Right? So what can you say about delta V across the capacitor? Of course, equal to the potential difference across the battery. Justification is very simple. Look, our circuit consists essentially of two big pieces of metals. This one, imagine here the line between these two electrodes, right? So this left side piece of metal on the left side, and here on the right side another piece of metal. And when the capacitor is full, so this metal and that metal will reach electrostatic equilibrium, where electric potential is exactly the same at every point. So it means that if you have here plus 6 volts on this side, so each point on this of this conductor is going to be at plus 6 volts. Then this side will be at minus 6 volts. So over here will be minus 6 volts. So every time, if a capacitor is connected to the battery, potential difference across the capacitor equals to the potential difference across the battery. It doesn't matter what you do with the distance between the plates, unless if you just don't touch them. Okay. Yeah. Okay. Okay. Look, if I draw this part, you see? And then if I draw this part. So essentially it's two separate pieces of conductors, metals, right? You see? Because again, it's electrode of the battery, this wire, that electrode of the capacitor, it's just one piece of metal. They're all soldered together, right? So, and when the capacitor is full, so charges stop running, so this piece of a conductor will reach electrostatic equilibrium. What's so special about electrostatic equilibrium? Every point inside of the conductor has exactly the same electric potential. And that electric potential is determined by what? By the battery. It's our active source. Since we have 12 volts potential difference, so on this side, let's say we have plus 6. So it means that every point of this piece of a conductor is at plus 6 volts. Then exactly the same logic I can apply to this piece of a, to this part of the circuit. This piece of a conductor, again, piece of a conductor, exactly the same piece of metal. And the electric potential is determined by this electrode of the battery, minus 6 volts. So pretty much every point on this side is at minus 6 volts. Just a second. So every time plus 6, minus 6. Even if you increase the distance or reduce the distance between the plates, potential difference is going to be exactly the same. Of course, provided that your battery is healthy enough, right? So, no, it's impossible. If you connect the battery, so battery will determine. So it's impossible to have different electric potential. It can be different if you disturb it slightly. Let's say you reduce the distance or increase the distance, but you have to wait for maybe microsecond, nanoseconds. You need to wait for a short period of time so that those conductors will reach a new electrostatic equilibrium. And the electric potential will be plus 6, minus 6 all the time, but you need to wait for a little bit.
So electrostatic equilibrium is equivalent to the capacitor.
It's not electrostatic equilibrium, not, it's just about, it's a property of a conductor.
Yeah, I meant with this situation.
Yeah, so I applied that piece of physics which we discussed like a month ago to the capacitor. Okay. At least that's how in my recitation classes I justify it. So he was sitting and nodding, right? Right. Okay, yeah. It's still in the process of reaching electrostatic equilibrium. You need to wait, as I said, you need to wait for a short period of time until electrons will finish doing their job, right? Making electric field inside of the conductor 0 and making electric potential constant at every point, right? So you need to wait a little bit. And that process, when it's all big mass, we're not discussing. Okay, anything else? So pretty much over here, as a result, we can write that delta V across the capacitor, let me call it delta V1, equals to delta V across the battery. Right? It's a basically more or less obvious fact, but I just wanted to justify it. Okay, so now after that, after discussing delta V, now again Q will be at the end. Now C, what can we say about C? Can we find C capacitance? Geometry is given, and capacitance depends only on the geometry. It doesn't care what's the electric field or potential or charge. It only cares about the geometry, right? Parallel plate capacitor, epsilon naught A divided by D. So let's find C1 equals to epsilon naught A divided by D1. I don't add any subscript to area because it's exactly the same in all parts. Right. Okay, so you can plug numbers. I'm not going to do it. I will just remind you that D1 must be, I didn't give you D1. Ah, no, it's here, 2 millimeters. Must be converted into meters. So this must be 2 times 10 to the power of minus 3 meters. Okay, I'm not going to plug numbers. I will send you my notes. You can calculate by yourself. I know you do it very fast. So you're going to get 11. You know what? I added too many sig figs. Okay, 11 times 10 to the power of minus 12 farads. So it's a picofarads. Prefixes will be again given on the formula sheet at the end of the formula sheet. Now I started adding a table with prefixes, right? Because you're still learning, you're still trying to remember those. Okay, so capacitance found, and now finally charge, the third quantity. So now using this formula, we can find capacitance. It's a C times delta V. So capacitance, so now Q1 will be equal to C1 times delta V1, right? It's just application of these two formulas. Okay, so again, you can plug numbers. So this is 12 volts. I can also add, since number is given. And so Q1 is 1.33 times 10 to the power of minus 10 coulombs. Again, guys, if something is not clear in terms of my handwriting, tell me. Because sometimes students see some question marks, strange in my notes. Okay, so now part B. Wait, it's just a simple step. Now, what if we reduce the distance? So, battery is still connected. Battery is still connected. And let's say now distance D2 will be equal to D1 divided by 2. I know, we put the rubber gloves and reduce the spacing between the plates by a factor of 2. Right. Okay, maybe I can draw quickly. So now it's a D sub 2. And still battery exactly the same. Delta V, of course, the battery. And the same question. Let's find now this time charge. So let's find Q2. No, actually, it's not the question about finding charge. Actually, we need to answer the question, what's the amount of additional charge that will come from the battery into the capacitor? Right. So let me write in words, probably. It's not Q2. It's not just Q2. Of course, we will have to find Q2. So we need to find additional charge that will appear in our capacitor. So we're going to reduce the distance, and we expect the charge will be increased in the capacitor. So I actually want to answer that question. So what will be that amount of additional charge? So, and now basically to our discussion, guys. So now we reduce the distance between the plates, but what is going to happen to the to the potential difference across the capacitor? Now I reduce the distance between the plates. What will be the potential difference? Will be exactly the same, because I can run exactly the same analysis. So this piece of a conductor reach electrostatic equilibrium, this piece of a conductor reach electrostatic equilibrium, and so potential difference will be equal to the potential differences across the batteries. So in this case, delta V2 will be equal to delta V1. So you need to realize that. But quite often we also discuss the second situation. What if during this transition we remove the battery and then reduce the distance or increase the distance? Which quantity will be exactly the same? Which quantity will be will stay the same still? You remember? Yeah. I'm not asking you guys from my recitation classes, because I'm sure that you know, right? You know the answer. Okay, now, sort of not related to this question. What if during this transition from part A to part B, when we reduce the distance between the plates, what if before that I disconnect the battery? Which quantity will stay the same during this transition from part A to part B? Again, three quantities. It's a C, Q, delta V. No, we disconnected the battery and then reduced the spacing. Okay, he was first. And I'm not asking you guys on purpose, right? C. Okay, you remember I told you what's the major feature of this formula, C? It depends on the geometry. We changed geometry, D is smaller. So C is not going to be the same. As a result, why? Yeah,
the charge is going to be the same on each side.
I know, Nikolai, right? So you in my recitation class, I know I bugged you about that, right?
The charge is still going to be the same on each side after you disconnect it.
Basically, yeah, the explanation is almost correct. Oh, not almost correct, right? Basically, the charge is trapped inside of the capacitor. So you charged it, and then you disconnect the source of charge. Battery is disconnected. It's sort of like I use this analogy with the ocean liner. You load it, let's say you load 1,000 people on the ocean liner, right? Let's assume that they are not depressed, they are not good swimmers, they are in a good health. And if I ask you what will be the number of passengers on that ship after 1 day of trip? Exactly the same, 1,000. Why 0? Come on.
Titanic,
No, okay, well, no, okay. The ship is in a good health also, right? And no, wow, Titanic. Right. So will be exactly the same, right? Although they might feel sick, they might want to get out, but they are trapped. Right? So it's exactly the same story here. Battery disconnected the source of electrons. So pretty much, and then it doesn't matter. Of course, if you wear rubber gloves, no charge cannot escape through humidity and so on, right? So charge will be trapped. Charge will be exactly the same if battery is disconnected. So if battery is connected, potential difference stays the same. If you disconnect the battery and start playing with the capacitor, then charge is going to be the same, right?
So if this question is on the exam,
Possible?
Well, yeah. Would it specify whether the capacitor was tampered with after or not?
Of course, we assume that we don't do, it will be written, we're going to tamper it, increase the distance between the plates, reduce the distance. Of course, that information will be given, right? Okay. And of course, I will also say what happens to the battery, right? Okay. Are we keeping it or we're removing it, right? Again, this comes from the logic. You just analyze what happens to the system. So it doesn't come from formula, some kind of formula, right? So this from some simple, okay, or not so simple logic. But in this case, battery is here, so potential difference stays the same. And so after that, we just need to repeat similar steps one more time. But again, I just wanted to discuss these two pieces of physics, right? Charge and the potential difference. Okay, so now after that, C2, which is going to be different, yeah?
You said
Yeah, yeah. And that's why I told you I didn't put any subscripts next to A because it's the same, right? Changing area of the plates is not that simple. It's a metal work, right? Okay, so C2. So it will be epsilon naught. Area is the same, and now D2. And of course, guys, from my recitation sections, you know I hate crunching these numbers. I will I will try to recycle the result from the past, right? I'm saving the world recycling stuff, right? Okay, so D2, it's a half of D1, epsilon naught A and D1 divided by 2. So this factor 2 goes upstairs, right? You know how to deal with fractions. So it will be 2 epsilon naught A divided by D1. And epsilon naught A divided by D1, it's a capacitance in part A. So it will be, so this is C1, so it will be 2 times C1. So we double capacitance, right? We double capacitance. Right. Okay, let me check. Yeah, of course. And so now, again, three quantities all the time. CQ delta V, we know C, we know delta V charge. So Q2 equals to, so it will be C times delta V. C2 times delta V2, right? And again, I don't want to plug numbers. I will still use those. So this is 2C1 times delta V. Delta V2 equals to delta V1. So I replaced. And C1 times delta V1, it's a Q1. C1 times delta V1, it's a Q1. So this is Q1. So it means that our charge is going to be doubled. And still, I don't want to calculate even these numbers. I'm so lazy. Right, since we want to find additional charge, so that is Q2, final amount of charge. So in order to find the amount of charge which came from the battery, so we need to take Q2 and subtract Q1. So additional charge. Right, so this is the final charge, that was the initial charge. So now let me write this way. So additional charge. Okay, I can write delta Q, or which way I wrote it. Yeah, delta Q. So it will be Q2 minus Q1. And so Q2 is a 2Q1 minus Q1, so that's why I didn't calculate any numbers. 2Q1 minus Q1, it will be equal to, so exactly the same amount of charge as we had in part A came from the battery in the second part when we reduced the distance between the plates. You reduce the distance, additional charge came from the battery. If you increase the distance between the plates, charge will go down. It means that the charge goes back to the battery. Basically, you recharge your battery. So you discharge it and then recharge it, discharge it, recharge it. Right. Okay, so again, something similar we had in our recitation classes. I just wanted to refresh it. So let me check all the gears. Okay, recording. Still recording. Yeah.
I have to say, I've never seen this in any of my
Like a secretary announcing. Press secretary.
I've never, like, I've attended most of my recitations, and I don't think I've seen it, like, played out this smooth before. Not to complain about my recitation professor. I'm just saying.
Okay, right. So that's why we have exam review.
Some discrepancies in the curriculum here.
No, we. Okay, no comments, right? And that's why we have exam review sessions, sort of to bring you to the common denominator, at least, right? And also lectures, right? Where, but of course, I cannot cover everything in the lecture. No. we justified the charge will be definitely the same because the charge which came into the battery originally now is trapped inside. Then just a second. So charge will be the same. Then capacitance, it depends on the geometry, so definitely will be changed, right? So this is the same, this is different, and then delta V must be different, right? It's sort of difficult to imagine, but logic and physics tells us that the potential difference is not going to be the same, right? Okay, so enough about capacitors. And I don't want to discuss equivalent capacitance because just a few days ago you had your quiz, right? So pretty much we tested, we pushed you about that, so I don't want to do that one more time. So now resistors, all right, currents, resistances, so pretty much this section, right? And okay, you know what, I will use this part of the board. And first, a couple of conceptual questions without getting deep into the calculations, right? So, conceptual question, right? Okay, now I will draw something ugly, right? Really something ugly, right? All right, so, and let's assume that there is a potential difference, and there is a, okay, potential difference. We apply a potential difference. So, delta V. And of course, as a result, current will flow. If I measure current, let's say, over here in this cross section, or over there in that cross section, right? What can you say about currents in that or this case? If I measure current over there or over there, current is going to be the same. Current is going to be, it doesn't matter how ugly or nice or elegant your, just a second, your piece of wire is. It doesn't matter which cross section you take, current must be the same. It's like, again, nice analogy if you compare it with water, since it's almost impossible to compress water. So when water flows through the pipe of this cross section, of course, here it is going to flow faster, giving us, let's say, 5 liters per second. But over here, it's a cross-sectional area is large, so it's going to flow slower. But because of the large cross-section, it is going to give us exactly the same 5 liters per second. So it's a nice analogy in order to sort of justify the current. Oh, who wanted to ask?
Don't worry about it.
Okay, okay. Right. Okay, great. So current is going to be the same. So let's say over here, section A and part B. So in this case, current in that part and over there will be the same. So current is the same. If there is no junction point, current stays the same. But what about current density? Current density. Right? Yeah. Since here is the definition of current density, I over A, since currents are the same, so pretty much in the part where cross-sectional area is smaller, is going to give us larger current density. So current density is J equals I over A. So this will be I divided by A sub A. Current divided by A sub B. I didn't expect this. I'm just making it up. Right. So since here area is larger, so this is going to be smaller. Right. Yeah. Right. Okay. It's again just to remind you. Usually, after a few times, if you're a few cases like this, students usually remember that, no problems. So now, the next conceptual question. I give it, yeah. J current density. At the back, can you hear me? Okay, good. So the next conceptual question, actually, it's I gave this question, I think, a couple of semesters ago on one of the exams. All right, so let's say we have this collection of resistors. So let's say they're all the same, for example. And this is point A, and this point B. And the question is quite simple. What can you say about equivalent resistance between points A and B? I see you. What will be the equivalent resistance? I hear you. A kind of loop. I thought, okay, I will ask you. So no, I'm not asking you. I'm familiar with you. Okay, so what do you think? Yeah. Okay, guys, I see. You see the answer? What will be the answer? You don't see it? No. Okay. All right. So he said 0. He said 0. He basically said essentially the same. Why is it 0? Okay. In my recitation. Okay. I got it. Thank you. I answered your question. Okay. In my classes, recitation classes, I give this justification, right, to make it. I think it's absolutely clear, right? Like. Okay, guys, you know that I was asking you. So, entering this room, we have not just one option. There is an option of through the door. There is an option through the window. There is an option through the walls, right, through the ceilings, and so on, right? They're all options. Absolutely, okay, not legitimate, but not options, right? You will be handcuffed, right? Then, and maybe when you enter this room through the wall, undertaker will take care of you, right? So, right. So, but anyway, these are all options. But what's the difference between them? Resistance, of course, the amount of resistance that we are going to experience, right? And since we are all smart, we have brains, of course, we pick the option with the least amount of resistance. We just go to the door, open it up, and enter. Here, electrons, when they come to this point, they have three options. Either going and crushing their skull through these resistors too. It's quite a resistive option. Or they can go this way. There is only one resistor, but still significant amount of resistance. Or they can go through open door, no resistance. Although electrons, they don't have brains, but their behavior, especially social dynamics, our social dynamics and the dynamics of a multi-particle system, almost identical. Although they don't have brains, but whenever they come to this situation, they will pick the least resistive option. And they will all go this way. So these two resistors and that resistor will be just ignored. They will be bypassed. They will be bypassed. So of course, you can see that equivalent resistance will be 0 because they go through the 0 resistive option, right? And when I gave this question in one of the exams, plenty of students calculated equivalent resistance, and it was not 0. It was like, I don't know, 25 or 30% at least, right? So calculated, right, using all those formulas, right? But in this case, 0 immediately without any justification even, and I can buy that because it's kind of obvious, right? But of course, it needs to be discussed at the very beginning. Make sense? Will be 0. Okay, great. Enough of these conceptual questions, and now one problem. Physics with mathematics mixed. I forgot to ask you justification, right? So I just drifted away, sorry, because my original sort of intention was to come back to you and ask for your justification why the equivalent resistance is 0. And I forgot, sorry. Okay, so let me erase this part and the next question. Ah, yeah, I didn't write the answer. Oh my god. R equivalent equals to 0. Right. Okay, now. So now part 4. Pretty much I want to play with this formula. I used to discuss at the very beginning the problem like this in in lectures, and then I drifted away from this option. So now I decided to add it to this exam review session. So we have a long cylindrical resistor. Okay, wire. Of course, it has a normal wire. Any wire has some amount of resistance. Okay, let me draw it. And so let's say the length is L. All right, so we have a copper wire. Right. The total resistance of this copper wire is given. R total equals to 10 ohms. Kind of too much for a copper wire resistance, right? Usually it's around 1 ohm maximum, right? A 0.1 ohm typical. But then nevertheless, let's say 10 ohms. So, and let's say we are poor researchers, right? Lab doesn't have much funding. So we want to get 2 resistors out of this resistor. So we want to make a decision. Where should we cut this wire? Cut where? So that we will get 2 resistors, and this resistor R1 will be 4 times larger than that resistor. Okay, so now over here there will be a first part. Okay, this is our cut. This will be R1 equals to 4R2, and this is the resistor R2. We just wanted to get 2 resistors out of 1. So and the question is, where should we cut it in order to have here 4 times that? And what else? Yes, so I wrote that down. So let me write it here. So R1 will be equal to 4R2. All right, so where should we cut it? Inwards. So now let's convert all these questions and everything in symbols into mathematics, right, and physics. Right? So let's imagine, okay, so this is our cut. And let's introduce an unknown. Okay, so let's call this is x. Essentially our unknown, but we assume, okay, so this is point for the cut, and the distance to that cut is x, unknown. So we're introducing our unknown into the problem. And of course, this length will be L minus x, obviously, right? And it looks like we have everything. Of course, we can assume that cross-sectional area is A. It's not given. But if we need to introduce a certain constant, we can do that. Most likely, it will disappear at a certain point. So what else? And of course, we can assume that some resistivity is given, right? So let's say some rho copper, yeah, you can find, but we don't need actual number. Resistivity. Okay, and so what? Now let's start, based on what is given, let's start rolling, hoping for something good. So this is a piece of information which is given. So let me start from that. R1 equals to 4R2. And then how can we find these resistances? How can we write? Which formula can be used? Where is it? Right. In our recent recitation class, we used that when we discussed power, right? And plenty of students forget about this formula. Right. So R equals to rho L over A, right? So we're going to, of course, okay, L, okay, so since we have that L, no, I don't like this. Let me use L capital, for example. Different symbol. Because in our problem, L small is already used, so we need to use something else. And so how can we write R1? It's a rho A, and what is L for R1? It's X. It's X. Right. So it will be rho X divided by A. And then 4 times R2, it will be with L minus X, right? Because that's the length of the second part. Right. So L minus X divided by A. Right. So we just started from what we know, and we're just now moving with the flow. Of course, resistance. Wait, resistivity. Over here, there should be resistivity. Right? I was thinking about L minus X and forgot about resistivity. So resistivity goes as it should be. Then area also goes. That's why they were not given in the problem. As a result, we have that X equals to 4L minus X. Okay, we're getting the equation. Nice. One equation, one unknown. It looks like we should be solved. Of course, in terms of L. Of course, it will be written in terms of L. Okay. So X goes to that side. X plus 4X equals to 4L. So 5X equals to 4L. Now the simple mathematical manipulation. So now X will be 4 over 5L. X equals to 4 over 5L. 0.8L. So it is 0.8L. So essentially what it means? It means that 80% of the wire must go to the first resistor, and 20% of the wire goes for the second resistor, right? So it means that, all right, which way I wrote it? Okay, 80% of the wire is for R1, and of course 20% for R2. Okay, so now actually, essentially the problem is solved, right, based on what I wrote. But let's actually find the resistances R1 and R2. Right? So now let's find R1 actually and R2. Of course, you can easily see the answer, but I still want to using this formula. So R1 equals to rho X over A. I just rewrote this, right? X is 0.8L. So it's a rho times 0.8L over A. So I can rewrite it like this, 0.8 rho L over A. Rho L over A, it's our total resistance. It's a total resistance, the total length of the whole wire, total resistance. So it's a R total. So it will be 0.8 R total. R total 10 ohms. So 0.8 times 10. So it will be 8 ohms. Of course, you could tell it from the very beginning when we found that 80% of the wire goes to the resistor R1. So it's obviously 8 ohms out of 10. Okay, and exactly the same. So R2 will be equal to the rest. So it's I can write R total minus R1. Of course, it will be 10 minus 8. It will be 2 ohms. 2 ohms. Again, I used to solve this problem in the lecture, then abandon it. So I just wanted to play with that formula a little bit, right? Because I noticed that some of you forgot based on my previous recitation class. Now it's going to be the long one. Okay, any questions about this? The long one, it means that it will be about the equivalent resistance. So, and after that, we will move to Kirchhoff rules. And after that, RC circuits. RC circuits. So we're getting closer to the midpoint. Power and RC circuits. Okay, so then I will start erasing this if you don't have any questions. So I will erase this. So it will be number 5, then 6. Yeah. So 5. So we need to analyze this circuit. And I'm thinking, which way should I draw it? Top. Okay, let me draw it from the top to the bottom, right? So my circuits are going to be in the middle, and then I'm going to write on the left, on the right and on the left side. So equivalent resistance. So first there is a battery, then there is a resistor over here, then next resistor over there, then 2 more. And let me connect them like this. Oh, you know, it's too, these wires are too short, it doesn't look good. Okay, this would be better. So now values. So let's say delta V of the battery is 24 volts. Then R1, R2, R3, and don't laugh, R5. It's still mysterious. When I was writing down, preparing this problem, I think in the previous year, right? For mysterious reason, R4 was missing, and then I decided, okay, so let it be. Yes, so that's why I told you don't laugh. It's still a mystery for me why my brain decided to skip R4. Right. Our brains are mysterious things. All right, okay, so now the numbers of these resistors. Let me write them separately. And. Yeah, we'll write that here. So R1 equals to 6 ohms. R2 equals to 12 ohms. R3, 4. And, R4, R5. R5 equals to 2 ohms. Right? Okay, so that's the circuit. And the question is, you remember, analyze this circuit. So what does it mean, analyzing circuit full of resistors? Again, circuit trinity. In this case, now it's 3 different parameters, R, I, delta V. If you know those, you know everything about this circuit. In this case, resistances are given, so it means that we need to find potential differences and currents. So potential differences across each of these resistors and currents across each of those through each of those resistors. So we need to find, let me write that here. So find I1, 2, 3, 5. Just lazy to write I1, I2, so I just use comma next to subscripts. And then delta V's 1, 2, 3, 5. Actually, the missing resistor adds some flavor to the problem. It's boring when everything is smooth and nice. It's Friday, I'm just blabbing too much. All right. Okay, so let's start analyzing. So, and you remember the steps. First, you need to simplify the circuit to the simplest possible, and then find something. We'll see what can be found, and then we will start moving, and everything, the whole analysis is over here and over there in these two red boxes. So let's start moving. So first, any two resistors connected in series or in parallel? Any? Yeah. To start somewhere. Which? R5. It's a nice 5, right? So, okay, guys, you're making me feel bad. Right? So, R5, the top one. R5 and R3, of course, in series. So, these two guys, of course, in series. And again, so why? Why are they in series? There is no junction point between them. So it means that current is going to be exactly the same. And that's the major feature of things connected in series. Current is the same. Current is the same. And then, of course, R1 and R2 in parallel. Again, why? Because potential differences are the same all the time. It doesn't matter what you do with the rest of the circuit. Potential differences across these two resistors are going to be the same. So these are, of course, in parallel. So we're making two transformations in one step. Yeah. Awesome. I like the questions like this. All right. Timmy. Yeah. No, no. It's not zero, so of course it will be, they will not equal, but majority will go through majority. Right? Majority will go through the entrance with less resistance, and of course, minority will go through the resistor with less resistance. Right? So there will be some split. Right? All right. So let me redraw first this circuit, and then I will, of course, calculate. And of course, the battery works in exactly the same way, right? So it will be the same delta V. And now, which way I drew it? Okay, on the one side. So this will be R35 and R12. Of course, subscripts are self-explanatory. Right? So R35 in series, we just need to add them. It's the easiest. So R35 equals to R3 plus R5, right? And that's 3 and 5, 6 ohms. And in parallel, okay, I don't like that, but that's life. 1 over R1 plus 1 over R2. And I like your comments about Titanic. Now it's in my head. So now I need to add to my story the statement about that. Okay, so now, of course, you can bring to the common denominator or whatever you feel like. So R12, I will just write down the answer. It will be 4 ohms. Right. Again, don't forget to flip every time because it's very, very silly mistakes and it happens. So now after that, obviously I'm not asking anyone. These two guys, of course, is in series, right? So we can replace them there are no any single junction point, of course, current is exactly the same. Current the same, it means device is connected in series, right? And so we can redraw immediately this circuit to the simplest possible. So equivalent circuit, final equivalent circuit. So it will be R equivalent and exactly the same battery, delta V. And so these are equivalent, of course, sum of those two. So R equivalent equals to R12 plus R35. And that's why I like Richard Feynman's. He was so awesome in terms of finding these analogies, right? So comparisons, right? So he was brilliant in that case, right? And that's why we like his books, right? So 6 plus 4, 10. 6 ohms plus 4 ohms, 10 ohms. Right. Okay, that's equivalent resistance, sorry. Equivalent resistance. And so now we have the simplest possible situation. Potential difference is given, resistance we found. We can easily find current using Ohm's law, right? Current using Ohm's law. And now let me write expression for the resistance, right? So over here somewhere in the corner, because now we're going to use it a lot, right? So now we can find the current. So I. So it will be the total current taking from the battery. So now the total current. So I equals delta V over R equivalent. And again, delta V across the battery stays the same because that's how we develop the method of an equivalent resistance. We don't want to disturb the rest of the circuit. So that's why we can use still the same 24 volts. Okay, so 24 volts divided by 10 ohms. So it will be 2.4 amps. Let me check my notes. Yeah. I was afraid of that. Next time I need to bring some kind of cover, right? Some mat on top of that. Right. Okay, so now it's usually like making a crack in the wall, and now we just need to expand it and find what needs to be found. Right. And again, this current, it's over here and over there. Right. If I ask you from the very beginning in this circuit, what was the total amount of current taken from the battery, I doubt that you would be able to answer unless you can do these steps very quickly in your head, right? Like a computer. But slowly we get to this point. So now, since we found this, now we can move back finding what needs to be found actually. So now let's start moving back from this circuit to that circuit. And simple, you're using this piece of physics and that piece of physics every time. So since this resistor replaced these two resistors connected in series, which quantity is exactly the same for these three resistors? Current. I1 equals to I2 equals to I equivalent, and I equivalent we just found it's a total current. So now let me construct this first bridge. So I1, no, not I1, I35. I35 equals to I12 equals to I. So I rewrote this statement for our particular situation. Because in our case, two resistors connected in series, it's this and that. So current through this resistor equals to the current through that resistor and equals to the current through the equivalent resistor, which we just found. So that's I just rewrote this. And so it is equal to 2.4 amps. And let me emphasize, so this came from there. Okay, so that's, I usually tell students it's a bridge to move from this circuit to that circuit. And now we just need to use this bridge in order to find what? What can be found? Can we find potential difference across this resistor? We know current. We know resistance. Ohm's law. We can find potential difference. That's why I wrote down in that corner potential Ohm's law, right? Because now I'm going to use it over and over and over again, right? So now we're going to use the information from the bridge in order to find. Right. So first delta V. Delta V across the resistor 3.5. Delta V, it's Ri. So R 3.5 times I 3.5. And current comes from the bridge. R from the statement of the problem, current from the bridge. So numbers 6 ohms times current 2.4. Okay, I skipped units because I'm running out of space before my circuit. Wait, 6 times 2.4, it's a 12, 14. It sounds strange. Wait. Hold it. No, I found current, yeah. Yeah, 14.4. I was just looking at my wrong place of my notes. It's exactly the same answer. 14.4. Sometimes I doubt myself. Right. Especially at the end of Friday. So now exactly the same we can apply for R12. We can find potential difference across the resistor 1, 2. So delta V12 equals to R12 times current. And again, current, the value of the current comes from this bridge. Again, you can plug numbers. 2.4 and 4. 4 times 2.4, it will be 9.6. 9.6 volts. Okay, still, we made this step, and still we haven't found a single quantity which we actually need to find. But we've made progress. We made the progress. Now the next step, of course, we will start finding everything. So we exhausted this bridge. Nothing else can be done with that. So now we need to move from this circuit to that circuit, because inside of this there are 2 resistors connected in series. Inside of that there are 2 resistors connected in parallel. We need to extract that information hidden right now. Let me first start with the parallel case, I think. Yeah, let me start with these guys. Instead of R12, all right, parallel, their potential differences are the same. So I need to apply this bridge for our situation for this resistor R12. So delta V1 equals to delta V2, potential differences across resistors in parallel, equals to the potential difference across an equivalent resistor, which replaced them. Right? So it is equal to delta V12. And delta V12 we found in the previous step, right? So it is equal to 9.226 volts. Right? So, and let me show that this comes from there. So that's our second bridge. And so now we need to exhaust it. So current, we can find current here, and we can find current there. Right. Okay, wrong color. So it will be I1 equals to delta V1 over R1. Delta V1 again comes from here. So exactly the same steps we are repeating. Different situations, right? So delta V1 9.6 volts divided by R1 6 ohms. 1.6 amps. Wait, and I ran out of space. I should have used smaller. Okay, let me try to squeeze over here so it's related to this part. So I2 current over here. So we know potential difference. We know the resistance. We should be able to find current. So it's a delta V2 over R2. Again, delta V2 comes from the bridge. So 9.6 divided by 12. Wait, no way, I'm not going to calculate that number. 9.6 over 12, 0.8. Okay, so at this point we can say we finished analyzing resistor R1 and R2 because we know currents and we know potential differences. R1 and R2 done, right? But we still have R3 and R5. So let's the last bridge. So in series, so it means that we need to write the same current. Currents are the same. The same currents. So I3 equals to I5 equals to the current through their equivalent resistance. R3, where is R35? So we're using that. Yeah. So now this time, of course, it comes. Okay, this information comes from the bridge, not from what we found over here. So I35. Okay, how should I run this line? So it is equal to 2.4 amps. Okay, I need the space. 2.4 amps. Right. Yeah. Okay, and the last two lines in this problem. So let's find the potential difference. Potential difference across this, because we know currents, we know resistance, so we can find potential difference. And the same about R3. So potential difference, delta V3, it's a I3 times R3. I3 comes again from the build bridge. So it will be 2.4 times 4, 9.6. 9.6 volts. Let me check. Yeah. And now delta V 5. So it's I5 times R5. Again, 2.4 times R5, 2. So it will be 4.8 volts. Done. So pretty much now we found all 8 quantities. All 8 quantities, right? So it's quite straightforward, right? If you don't like this method, of course, you can analyze like double department students, right? So what's the potential difference here? What's the current there, right? So it's yeah. Pretty much. Hmm? Yeah. Pretty much, yeah. It's a coincidence. It's yes, coincidence, right? If you change this resistor R5, okay, no, I need to look carefully, right? So I don't want to. Come on, right? So. Okay, this long problem enough, right? So now, Kirchhoff rules. You had a quiz just Wednesday, right? So let me just quickly write equations, right? It will take like a few minutes. Right. Or should I skip it? Yeah. Just for fun, again, you can look by yourself. Right? Okay, electric power then. So it's 2 hours. Okay, yeah, so 2.5 hours here. Okay. So I can erase this. Start erasing. So number 6 we skipped. So this okay. Let's keep an order 6. Flashlight bulb. Okay, let me check if everything is still rolling. Yeah. Battery is still alive. Oh, I lost part of my antenna. Okay, I'll find it later. All right. So there is a flashlight bulb, and a rating of that bulb is given. I think it's it produces 2 watt of power if you apply potential difference 3 volts. Then this battery is connected to a 9-volt battery, right? Wait, that bulb, I said battery, that bulb is connected to a 9-volt battery. So pretty much, we want to get that power which is stated by the company. So we want to get 2 watts. So it means that we need to dump somewhere, somehow, additional potential difference. So we're going to add a resistor in the circuit. And so now we need to calculate what should be the value of that resistor in order to get those numbers which company stated, so rated numbers, 2 watts with 3 volts. So pretty much I just want to add the resistor, calculate what's the value of that resistor in order to get the rating numbers of the bulb. So now let me draw the diagram and what is given. So it's basically electric power. Problem about the electric power. Right. So there is a bulb. And as I said, bulb rated, okay, with these numbers. So power equals to, okay, let me add subscript B. 2 watts when potential difference across the bulb equals to 3 volts. So, yeah. L, electric power. EL. You've been in my recitation class for months and a half, right? Attending all classes. No, of course, it's. I was lazy to write the whole word. All right. Okay. So now battery. And EMF is given, so EMF equals to 9 volts. And now I need to draw the circuit, and then I will write, of course, what needs to be found. So this is a battery. Here there will be a bulb. In my recitation class, actually, one student asked, so what's the symbol for the bulb? I even couldn't restore it. I practiced it in the office, and still I don't like it. It looks ugly. Whenever I draw it, it's too complicated. So I usually just draw a bulb. What? B. Bulb. Okay, so and now pretty much we just need to find the value of the resistor R to get these numbers. So the bulb would produce 2 watts of light. Let's assume that there's no heating, ideal situation. And the potential difference across the bulb, of course, must be equal to 3 volts in order to get that. So I can show that this is our delta V sub B. It's this, right? And this is our EMF. So which way I wrote the question? So we need to find R. So that we can operate the bulb um, at the rated values. At the rated values. So, there are a few approaches which are basically potato-potato, will be very similar, but still slightly different. So I'm thinking this way. If we want to operate the bulb with these numbers, can we find the value of the current that must flow through the bulb? Can we find the current? Yeah. Where is my power? Here. So power is given, potential difference we know which we want, right? And so we can find current. Of course, you can find also resistance, but as I said, there are slightly kind of different versions of the solution. I suggested let's find the current, right? And if we find that current, what can we say about that current? Current through the bulb will be, it's a current in the whole circuit. It will be exactly the same current because we don't have any junction points. So pretty much if we find that current through the bulb, it will be our current in the whole circuit. And it will be the current in our resistor, through our resistor, right? Okay, great. So let's find which way I wrote it. So the current through the bulb so I equals to, you know what, let me first write the formula for the power, right? So this, and then I will rewrite and solve it for the current. So it's a BB and current. So I just rewrote this formula, right, for the power. So current will be equal to power divided by delta V. So 2 watts divided by 3 volts. Wait, numbers are not nice, but 2/3 of an amp. Is it correct? Actually, in my notes, I even didn't calculate. I just dragged symbols to the very end and then plugged numbers usually at the very end. That's why I was kind of surprised with the number, because actually I didn't calculate in my notes. Right, and so, and that is the current in the whole circuit. So now, next step. It looks like now we need to involve all elements into one equation. So what can be applied? Yeah, there are different things, but I probably, I suggest, what about the loop rule? In the loop rule, so we have a loop. Of course, all elements will be automatically involved because we walk around the whole circuit counting all potential differences. So let's apply loop rule. So it will be, okay, in order to apply loop rule, so let me introduce the travel direction. So let's say this is the travel direction. And current direction, we don't have to guess or assume because we have only one battery. So we know current is going to flow this way. So that's the direction of the current. From plus to minus convention, you remember, right? Okay, so now we have all preliminary steps. Now we can start writing Kirchhoff loop rule. So we're traveling, travel direction from minus to plus, contribution will be positive. So it's a plus EMF. Then resistor, current direction that way, travel direction also. Both directions the same. Rule number 3, contribution is negative, minus IR. So it's a, bless you, again, minus I times R. And R is our unknown. We need to remember that, of course. And the last, potential voltage drop across the resistor, across the bulb. And do we know that number? Yeah, 3 volts. It was given. So we want to operate bulb under those conditions. So the potential difference, we want that. Pretty much we want to adjust the value of R to get that. So we're just imposing our demands. So it will, and of course it will be minus because it's just a resistor. Of course there will be voltage drop. So current direction that way, travel direction that way still. So we're going to get negative. So minus delta V across the, I use B system, B bulb. Okay, and of course it must be an equation, so it is equal to 0. One unknown, one equation. We just need to solve for R. Okay, so let's do it. That term goes to that side, and then I will flip the whole equation, so it will be I times R equals to EMF minus delta V sub B. Again, current we found. Remember that. So, and of course, as a result, resistance equal to EMF minus delta VB divided by the current. And, okay, now let me plug numbers. EMF 9 volts. 9 volts, then minus potential difference 3 volts, and current 2/3 of an amp. What are we getting? 6, 3, 18, 18 over 2, 9. 9 volts, right? Oh, 9 ohms, 9 ohms. Right. Yeah, 9 ohms. So if you attach a better resistor, 9 volt resistor, then the bulb is going to produce this power. There will be this potential difference across the bulb, and that will be the wattage of the battery, of the bulb. If actually, additional question, can we find resistance of the bulb? Easily, right? There are different options. You can use either power and the voltage, right? Or you can use just Ohm's law. Because you know delta V, you know current, and you can find resistance of the bulb using either power or Ohm's law, right? So easily. So you can find also resistance of the bulb. Sort of some additional question, right? Just bonus question. So delta V across the bulb divided by the current. Current is exactly what we found already. So it's 3 volts divided by 2/3. Wait, 3 volts and road 2. Oh my God. 3 volts divided by 2/3 of an amp. 9 over 2, 4.5 ohms. 4.5 ohms. So the equivalent resistance, the total resistance of the circuit is 13.5. Good. Titanic is still floating, right? There are so many stories. We're being recorded. You will tell me story after. Of course, I will cut it. I will. Okay, so now it's a conceptual question related to the power, right? And related to just recently what we discussed like 1 hour ago. What if we have 2 bulbs? No, I'm still going to draw a bulb. I have a circuit element over here. No way. Too complicated. So the first bulb is over here. Wait, that's an ugly bulb, but okay. So then over here there is a switch. And then there is a second bulb in this part of the circuit. Something like this. So bulb A, bulb B. Right. And this is the switch. S stands for switch, of course, right? All right. Any information about resistances? No. Just RA and RB. So this will be resistance A, resistance B. Assume it's constant, of course. So the question is very simple. First, the switch is open. There will be some power in the first bulb and the second bulb. Then we close the switch. What will happen to the power in both bulbs? So initially, S is open. So of course there will be some power in bulb A initial, and which is not zero, of course, right? And power in bulb B also initial, which is also not zero. They both glow. All right, both glow. All right. So now part B, final. So I stands for initial, F stands for final. S is closed. What can you say about the power in bulb B when we close the switch? What will happen to the brightness of bulb B when we close the switch? Still thinking? We discussed that like 1 hour ago, a very similar situation. And that's why I decided not to skip this question and push one more time. I see you, right? Quite familiar with you, right? I know that you know. Oh, Ellen. So, your opinion, what will happen to the brightness of bulb B? Any idea? And I will still get back to you. Also thinking? Still? Okay. So, when you close the switch, and now you remember, imagine electrons traveling this way. And now they have to make a decision at this point. Should they go to the right or should they go down? And you remember, they're very smart, like us. Although they don't have brains, right? Okay, I'm not insulting us. Okay, I will cut this out. Of course, it's an open door. Like us, we are not crashing through the walls, right? We all open the door nicely, right? And then hold the door to avoid that noise, right? Slamming noise. Of course, it means that all current, all electrons, right? They're going to go through the switch. No one wants to get through that resistance. All electrons in this case, because this is an open door. So it means that power in bulb B is going to be, huh? You said plus? Less, not just less. It's zero. It will be dark completely, right? Make sense? See that? Okay. Because again, it's at this point, none of the electrons would want to go through this resistance because there is an open door. So basically, this resistor, that bulb, is going to be bypassed. All the current is going to through this switch, and as a result, power in bulb B in the final situation equals 0. Right? Again, I just decided to push one more time. The more we push, it's sort of like a brainwashing. You know, it's in physics, right? You need to tell something 1,000 times, and then you will believe in that. But of course, we usually try to justify it. Of course, yeah. I saw that you. All right, so 0 power. And what can you say about the power of bulb A final relative to the initial power of bulb A? Okay, yeah, finally. course, it will become brighter, right? Why? Because over here, when the switch was open, the equivalent resistance consisted of this resistor plus that resistor. So the current was kind of smaller. But once you close the switch, this resistor is out of the game. So now equivalent there is only one resistor. Of course, current is going to be larger. All right. We assume resistance is the same, stays the same, right? So of course, it means that power will be larger. Yeah.
When the switch is open, do any of the electrons flow in that direction, or does it all go to the same pole?
When it's open,
Yeah.
okay, they will make some attempts, unsuccessful attempts. So there is nowhere to go. It's a dead end, right? So the rumors will be spread, right? So go to the right. Okay, I'm just bluffing. Right? It means that there is no current, right? So, of course, we understand that these are metals. Electrons are everywhere. You remember, any piece of metal has gazillion number of electrons, free electrons. So pretty much the electrons are where? And they talk. Rumors get spread very quickly. So that's the dead end. Don't go there. Yeah. No, of course, no. All right. Yeah, so we just discussed. So the power is going to be larger than initial situation. Okay, so that's conceptual question. And again, I was just wanted to talk about the electrons bypassing a certain resistor, current bypassing a certain resistor. Okay, it looks like the last. Let's just quickly solve a problem about RC circuit. And those problems are usually not complicated. Usually most of the students do reasonably well because it's usually mathematics, not much of a physics, right? So time is given, find the value of charge or current or potential difference. Or the value of charge is given at a certain moment, so you need to find that moment. And the variations of that. So now I create one of those variations for this. Yeah, that. And then we'll call it a day. Yeah, we finished this long ago, so I can erase this. So number 7, it's supposed to be 8, but we skipped one problem. So 7. So RC circuit, and this is charging case. Charging situation. So RC charging. Sometimes, not often, but sometimes students make mistakes because look, charge, function for the charge in charging case and function for the charge in the discharging case, they're different. So sometimes students just grab whatever formula is closest to them, right, and use that, and that can be sometimes a mistake. So carefully with that. All right, so let me draw the circuit immediately, and then so we have a battery, then resistor, capacitor, and okay, let me draw it here in the middle to make it look better. Right, so that's the circuit. So then battery EMF of the battery is given. Then flash you again. So R1, R2, and this is C1 and C2. Okay, so now let me give you numbers. Okay, they're actually the same, C1 and C2. So R1 equals to R2 equals to 2.2 kilo ohms. And then capacitance is C1 equals to C2 equals to 3.8 micro. That's my micro with a long tail. And potential difference of the battery, 12 volts. So we need to find the moment of time when current drops to gets the value of 1.5 milliamps. So we need to find, okay, the moment of time when current, so I equals to, let me label like I1. No, let me, T1 equals, we need to find T1 when current equals to 1.5 milliamps. Actually, first, before we start showing this problem, at the initial moment of time, once you close the switch, what can you say about the current? When you just close the switch, right? So what can you say about the initial, about the current at the very, very initial moment of time? I was afraid of that. I was afraid of that because it's a very, very. That's why you're not the first one. It's a. You remember a movie which I showed to you right in the lecture? That episode, not Gold Rush. Okay, whatever. Running away, run for the land or something like that, right? So at the first, when the gun sounds, right? So of course all those farmers like run like crazy to get their land, right? This is my land, this is your land, right? First, at the initial moment of time, current is the maximum possible, right? So it's a very, very common when students think it's a first zero because kind of gut's feeling tells you that slow start, right? But actually it's not, right? So it's a maximum, right? So that's why I stopped, and before we started discussing this problem, I started asking you this question, right? So it's so maximum. Charge, of course, charge in these capacitors will be zero because the initial moment of time they're empty. There is nothing, right? But the current, so these electrons they see empty capacitors. Of course, they start running like crazy. Maximum, right? And that's what I plot over here. So initial moment of time, current, maximum, and then decays exponentially. Right. What do we need to find? The moment of time. So let me also show on the picture, on the graph, what needs to be found. So let's say this is time, this is current, this is the maximum current, I naught, let's call it, and then it decays exponentially. So essentially, we don't know what's the maximum value of current. It means that we'll have to find it, right? So, and over here somewhere we have the value I1, and this is the moment of time T1, which we need to find, essentially, right? And so sooner or later, of course, we will have to grab this function for the current, and we will start analyzing it. So let me write it over here. So I as a function of time equals to I naught e to the power of minus t over tau. Okay, let me frame it because it's essentially the most important piece for this problem. So before we start searching for the maximum current and the moment of time t1, what else do we have to find as a preliminary step? Time constant, RC time constant must be found. All right, RC time constant. Let's first find tau. And of course, the difference between this circuit and that circuit, here we have one resistor, one capacitor. Here we have two resistors, two capacitors. But it shouldn't be a problem for us because we have equivalent stuff. We can find equivalent resistance, equivalent capacitance, and then time constant will be R equivalent times C equivalent, right? So tau will be equal to R equivalent times C equivalent. So let's find these equivalent values. Damn it. I should have positioned these two capacitors in parallel. Easier to calculate. Only now I realized, right? So R equivalent. Of course, it's just R1 plus R2. All right, so it will be, they're the same. So it will be 4.4 kilo ohms. So 4.4 kilo ohms. And again, in my notes, I didn't calculate. I just dragged the symbols till the very end. So C equivalent, 1 over C equivalent equals to 1 over C1 plus 1 over C2. Since they're in series capacitors, we need to deal with these reciprocals, right? Not very pleasant, but not that bad. So, okay, I'm not going to calculate. I'm not going to plug numbers. I will just write down immediately C equivalent. I didn't calculate. Since I told you, I dragged the symbols till the very end. So let me write like this. So C1 times C2, C1 plus C2. Students from my recitation classes, you know, they know that I usually drag the symbols till the very end, right? And then only plug numbers most of the time. Right. Okay, so now this will be equal to R1 plus R2 n times C1, C2 divided by C1 plus C2. Actually, did you calculate this? No? 1.9 microfarads. Okay. Cool. All right, so after that, we need to know this. So now we need the maximum current, the value of the maximum current. So this is the first bullet, now the second bullet. So I naught. So how can we find that I naught? It looks like you already started thinking, so that's why I'm asking you. Again, you need to imagine, right? So what happens? Okay, not imagine, analyze the situation. At the initial moment of time, since you're still thinking, so I'm trying to push you, right? The charge in these two capacitors, when you just close the switch, charge in the capacitors, 0. Potential difference across each of those capacitors, they are empty. There is no charge. Potential difference will be 0. Of course, 0. So all this voltage drop which battery creates is across what? These two resistors. Here potential difference is 0. Here potential difference is 0. So pretty much all this EMF across these two resistors. So how can we find current? EMF divided by R equivalent, which is R1 plus R2, right? So that's how pretty much imagine. So these guys are empty. Potential difference across this and this 0. And so as a result, let me write at T equals 0, delta V across capacitor C1 equals to delta V across C2 equals to 0. So EMF is across those two resistors. Those two resistors. Okay, so now we can write that using Ohm's law, of course, it will be EMF divided by R1 plus R2. Because in these problems, quite often you need to find either initial charge or initial current. Just imagine what happens at the initial moment of time. Right? Okay, so now let me separate this slightly. And now it looks like we're all set. We have this, we have that. We have I1, so we just need to find T1. So now back to our function. And of course, at T1, which needs to be found. At T1, which needs to be found, right? So it will be I at T1. Let me label it I. I already mentioned. I wrote I1. Right. So this equals to I naught e to the power of minus T1 over tau. So essentially, we just need to play with that part. One equation, one unknown. T1 is unknown, right? We just need to turn it inside out for T1. Okay, so I naught, I will move to this side in the denominator. So it will be now just pure mathematics. Then next step, we need to bring it down. So we need to take natural log of both sides in order to drop that power. So it will be natural log of I1 over I0 equals to natural log of E minus T1, right, over tau. So it will be just minus T1 over tau. Again, if something not clear, tell me. But now it's just regular math. Okay, so T1 will be equal to minus tau natural log of I1 over I sub 0. And again, like I said in my recitation classes, whenever I see minus in front of the equation or function, one of my first desires, how can I hide it somewhere? It just makes me feel uncomfortable. Negative values, you need to be careful with them. Right? So in this case, of course, you know the properties of the log function. Right? So you remember, if you have natural log of, let's say, minus natural log of x, it's a natural log of 1 over x. Right? Properties of the log function. It's a natural log of x to the power of minus 1. So that's how we can hide that minus in front. So we just need to flip this ratio. And quite often students don't remember that. That's why I sort of usually pause and remind you. So T1, can you still see it? Probably. Yeah, I lowered the table before the class, before the review session. So it will be tau natural log of I0 over I1. So tau we found, right? I0 we also, where is my I0? Ah, here. But I didn't plug the numbers. Right? So pretty much if you plug all the numbers, you will get 5 times 10 to the power of minus 3 seconds. 5 milliseconds. 5 milliseconds. Actually, guys, did you calculate maximum value of the current? What's the number? 2.7 milliamps. 2.7 milliamps. Okay. And it drops to 1.5 milliamps. All right, so it's okay, complicated numbers. I just wanted to compare with the time constant. Yeah.
Can I ask where that equation for I0 came from?
Okay, from our discussions, right, with gentlemen, right? So look, again, essentially, I sort of quietly in my head applied the Kirchhoff loop rule, right? So look, potential difference across this at the initial moment of time, when you just close, electrons are still here, they started running, they're on the way to the capacitors. Capacitors are empty completely. Charge is 0, potential difference across each of those capacitors will be 0. So there is no voltage drop across this capacitor, there is no voltage drop across that. So pretty much all this EMF is dropped across those two resistors. So R equivalent R1 plus R2. So that's the logic. So that's the problem, right? Again, philosophy of the problems, as I said, exactly the same, right? So value of something is given, find time. Time is given, find, but before that, sometimes you need to find either initial current or initial charge. Time constant, of course. All right, so nothing else can be done. Okay, it's what, 2 hours, 35 minutes. Yeah, like exam one review session, very similar to that.